in general, in the Zig ecosystem, we kind of tell people to use Comptime like salt. You just add a pinch to make the program more flavorful, but that's it. You don't go overboard.
I want to talk about Zig today. You seem the most obvious person for me talking to about Zig. I've heard great things recently from Jonathan, who was on the show a couple of weeks ago. So what is Zig, Loris? What involvement do you have with Zig?
So Zig is a programming language, a lower level programming language. It's part of the new wave of programming languages where there's an emphasis towards giving you access to, let's say, the raw power of the machine, but trying also to get away from some of the craft that has been accumulated, all the bad accidents of history that have been in the C++ ecosystem for the last 40 years plus. So that's kind of where Zig sits in the landscape of programming languages. As for me specifically, I work at the Zig Software Foundation. So the Zig project, the Zig programming language, has a 501c3 nonprofit foundation registered in New York, and I work full time. And my title is VP of Community. The title is meant to mainly appease companies that email us, so that they say VP in the signature line, and they say, "Oh, nice." So I don't need to escalate. But in practice, like the description of my job is to increase the total amount of effort being spent on developing Zig. That means helping with fundraising. That means, replying to emails, like interacting with companies. It implies also following what the community is doing, like championing community initiatives that I believe help people be more proficient with Zig, get more involved in the development. Everything that helps Zig grow a vibrant community, because from a vibrant community, you get more, interesting projects written in Zig. Maybe we'll mention some later. You get more interesting contributors. You get more donations also on GitHub sponsors, for example. So helping have these also non-technical side of the project succeed is for us very important, because we are an independent project. So Zig is there's a 501c3 nonprofit, as I mentioned, but we don't have big tech baking. We don't have anybody from Google, Microsoft, or the usual suspects in our board of directors, and we don't take money from them. So to be independent, we need to be successful, kind of on our own.
Okay, cool. Thanks, Loris. So a lot of people, particularly those outside the US, are going to be wondering what a 501c organization is. So can you sum that up briefly, please?
Yes, that's actually a very good question. So nonprofit tends to mean two things, right? One is that you don't pay taxes, and the second one is that the money goes towards the company's mission, and the company's mission is meant to be something that is beneficial to kind of society as a whole, ideally. The reality is that this definition kind of gets stretched a little bit because there's a lot of nonprofit foundations that are actually also, according to, I'm still going to use like American numbering systems. The numbering is basically which section of the tax code applies to you. So there's 501c6 foundations that actually do pay taxes. And they are more like what you would call a consortium, a trade association, where a bunch of companies come together, they pay membership fees, and they all lobby towards something that they believe is beneficial for the market. And while there's nothing inherently evil with that type of company, it is, I feel like in practice, most of the time, fundamentally different from 501c3. So the way I would say, like in a succinct way, we are a actual proper nonprofit where we cannot lobby. For example, a 501c6 in the United States can spend money lobbying. Like they can take money and then give it to politicians to, I don't know, in Europe, I guess we would call that bribing. In the US, they call it lobbying. But they can do that. A 501c3 cannot. So in our case, we are a organization where you can donate money. Like if you believe in the Zig project, you can donate money, and that money goes towards paying developers to work on Zig.
Cool, I see. Well, I can't speak for mainland Europe, but definitely here in the UK we have lobbying. It's something I would like to see removed from politics, because we have far too much lobbying by rich people, rich organisations, that's not necessarily in the benefit of the rest of us. Cool. So that's the 501c. You kind of implied there that you're quite a small organisation. You don't have the backing of the big company. So how big is the Zig Foundation?
The Zig Foundation is about 4 or 5 full-time employees, plus another, let's say, 6 to 10 people who can bill hours, let's say, as a rough approximation, like part-time. They don't really have a schedule. They can bill more than part-time. They can bill less than part-time. And it's actually up to them. But in general, the people really, spending an amount of effort comparable to a full-time job. That's about 5 people.
That's pretty awesome for a non-profit without the backing of big companies in this area. And you've got Zig to something that people are using and building real-world software with. So, kudos. That's pretty awesome.
We've been really lucky to be able to make it work. There's plenty of open source projects that, would be totally worthy of being supported, but for one reason or another, it didn't work out. In our case, it did work out.
I tend to believe that, you make your own luck in a way. So I think that there's probably a few people that have been involved, some of you that have been perhaps absolutely key to making that luck and creating the right opportunity, so like surface area for that luck to occur, probably. Cool.
Yeah.
I'm trying to be nice. You can take credit for it.
The way I see it, it's definitely a 2-part solution. One part is, the main part is that there is some technical work happening around Zig that is insanely innovative and really beneficial for everybody doing this kind of development. There are some things that are genuinely new and exciting, like maybe you heard about Comptime. Comptime is just one language feature. It's about metaprogramming, but it's a very refreshing take on metaprogramming, and people get excited about it. That's it's just one feature of the language. So I would say that overall the strength of Zig as a programming language goes far past Comptime. But Comptime is one of those interesting ideas that it's kind of somewhat novel, not completely novel. It's not something that never anybody has ever heard before. But the specifics of the Zig implementation are very sound and very nicely approachable. So people do get excited about it. About that. There's also more work around Zig that is very interesting. One is, for example, cross-compilation. People have been suffering from having trouble building C and C++ projects since forever, and yet everybody depends on those. Like if you're a Python developer, you are using C libraries. You just don't use them directly. Your dependencies use them for you. And Python does suffer from all the problems that come from building C and C++ projects, and there's a bunch of like, it's a very deep rabbit hole. So Zig really innovates in that sense as well. And so that's, I feel like, part one. And then part two is just making sure that people outside know that this is happening, because technical work of this kind, it's very exciting once it's like complete enough that it becomes actually usable and useful for people. But most people, like if you are a Python developer, for example, you will benefit from what we're doing, but you will not know that on your own. Somebody has to come and tell you. And so basically the second half of the story, you could say it's marketing, but in reality, it's just making sure that people know all the crazy stuff that's going on with Zig.
Cool. Yeah, I have heard a lot of complimentary things about cross-compilation and how much people are getting from that. The first one, do you say Comptime?
Yeah.
So can you explain to anyone that doesn't know, which includes me, what that is, please?
Yeah. So when it comes to metaprogramming, usually you tend to have the main approach is macros. So C and C++, let's say that you want to define an array. So a array of static size that goes on the stack. So it's not an array that you can dynamically change the length of. It's decided at compile time, and it's always going to be that. But in C, for example, you have to put a number there. You have to have like either like you put a 5, like a literal number, or you can put a variable, but it can't even be a normal C variable. It has to be a macro definition. So you can put a variable name in there, but it has to be defined in the macro system. In the macro system, it's literally search and replace pretty much. It also has some logic to it, but it's mostly text replacement. And that's one way of doing metaprogramming, but it has some severe limits and surprising foot guns that you can get from macros. So in general, macros are not really a particularly loved way of doing metaprogramming. You can have better behaved macros. So for example, Lisp is famous for having good macros. Rust also, as a more modern language, has macros, but their macros are way more sophisticated than just text replacement. So for example, in C, you could have some unexpected side effects when you don't put parentheses around things because the text replacement replaces things in a way that you didn't expect necessarily. That does not happen with Rust, for example, nor Lisp. And so that's a little bit better. But there's still a problem there because macros are very powerful, but they force you to think about metaprogramming in terms of syntax. There's also other metaprogramming tools, like, for example, generics, which is more limited than macros. But with generics, you can say, I have this tree or like this data structure, this container, and I can parameterize it by type. So I can say this is a list of integer, this is a list of strings, this is a list of person, a list of whatever type you come up with. And that can be very nice. C++, for example, has templates, which are a particularly flexible way of doing that kind of metaprogramming, not just strictly generics, but it's, I would argue, mostly that. Templates also comes with its own downsides. Specifically, I would say in general, when it comes to generics and also templates, it's a sub-language in your language. Anybody who has used, for example, Java or C# or, well, C++, you know that you open diamond brackets and then you start using a different language inside the diamond brackets because you have to explain these constraints in a declarative manner. It's not your normal language that you're using. So now let's talk about Comptime. Comptime is basically the ability to run Zig code to do everything that you would do with templates, basically, or generics and more. But you do that with the language itself, manipulating data. So for example, if you want to create like a generic list, a list that can be a list made of different types, then what you do is that you create a function that you can call list, for example. That function takes as input a type argument and returns a type. And in the body of that function, you define a struct that contains, all the pointers that your list needs to have. And then you can say that the payload is the type T that was passed in as an argument. And that is not amazing. Just this example, it might seem like a minor change. But the fact is that from here, you can build a lot of metaprogramming logic that is not constrained to a different language, but you can use Zig itself. So let me give you just one, in my opinion, quintessential example of this. Let's say that you have a equal function that you want to be case insensitive. And you know that you will always use that function to compare a known string, so a string that you hard code in your program, against a string that has been provided by a user. So you can imagine that you're doing a case-sensitive match for like a subcommand or like some kind of query command. Well, if you in Zig, what you can do is that you can specify that the first argument has to be Comptime known, because the assumption is that we are going to use this function only to test user-provided strings against strings that we know already at compile time. And what you can do to enforce the invariant, and let's say that your comparison algorithm can benefit from the fact that you know that the hard-coded string every time you do a comparison, the one that is not user provided, you always write it in your program in all caps. So to enforce that constraint, what you can do is that you can test at Comptime that the string is actually uppercase. So, and how does that look like? Well, you just say that there's insensitive equal function. First argument is going to be a Comptime known string, and then in the body of the function, you literally loop over the string character by character. And if you see a lowercase letter, you can emit a compiler error that says the first argument is expected to be an all caps string. That is something that you can enforce at compile time. It has zero runtime overhead, and it's something that I believe I hope it's impossible to express with templates. I fear it might not be impossible. I fear it might be possible, but in an extremely cursed way.
Yeah, I can imagine that with some of the more recent features of C++, you might just be able to do that in templates. I would not want to debug it or try and read it.
Yeah, the general gist in Zig is that you just use the language. To be fair, you can abuse Comptime. Comptime and all forms of metaprogramming, you can put too much. You can make it complicated. You can make it, overly complicated in general. But so there's there's a warning where people should, that we, like in general in the Zig ecosystem, we kind of tell people to use Comptime like salt. You just add a pinch to make the program more flavorful, but that's it. You don't go overboard. But it's very clear, and like the way you express things is, in my opinion, significantly clearer than macros or templates.
That sounds very cool. I want to take a look at that now. I need some time to explore. Cool. So what are the other benefits then of using Zig? So it's great cross-compilation. You've got this innovative feature with Comptime. What else would you highlight as the kind of 2-3 best things about Zig that should make it interesting to people?
Well, when it comes to cross-compilation, one important thing to point out is that it's not just cross-compilation of Zig code. That's obviously nice to have. But more importantly, Zig is also a C and a C++ compiler, and it supports cross-compilation for those languages as well. So that means that you have a C library, you have a C dependency, and you can take that C dependency. You have to do some work because out of the box, C projects usually do not support cross-compilation. Like their build system, their makefile, their CMake, or whatever they use, usually doesn't support the ability to compile from a Linux machine to a Windows machine or whatever. But after you do that work, basically you have to implement their build script in the Zig build system. At that point, then the C project can be cross-compiled alongside the Zig code in a completely transparent way. The way this works is basically I guess it's like twofold. The one side is the Zig compiler and the Zig build system has this concept of cross-compilation as like a main use case. So all the APIs are designed to support that use case. So it's not like C build scripts are against that. They just don't prioritize it. And so people usually don't do all the necessary steps to make that work. And the tool doesn't make it super easy. The second half is that Zig provides a ton of utilities that you would need to compile for another platform that usually you don't have at your disposal, that you would have to go fetch yourself. So for example, if you're on Windows, you don't normally have a copy of glibc. You don't have a copy of Muscle, which are C libraries for Linux. And so at the very least, you would need to fetch those, put them somewhere, and expose them to your C compiler, because that's basically another dependency that you need to have. And Zig comes pre-bundled with those. Like they are in the Zig archive, so they're always available to you. So the point then in the end is that you can basically use Zig to take ownership of C dependencies, and they stop being this, black box, scary, it works now, better not touch it, because if it breaks, there's no solution, right? Now it's different. Now it's code that you can bring with you around. It's not any worse than the rest of your code because it cross-compiles. You can, for example, debugging obviously works across languages. So like you can load a debugger and you can have these stack traces that go from Zig into C, back into Zig, whatever. And everything works fine. And so now the C dependency, while yes, it's C code, so maybe you don't love it. Usually I don't love the code of my C dependencies. But if the C dependency does what it's supposed to do, then it can be, very well behaved citizen of your ecosystem. And ultimately, the end result is that basically you can use Zig to write software that is more portable than what you would be able to do otherwise. You can integrate with C libraries in a more intimate way, and it really helps you write higher quality software, in my experience.
So does that mean that if I've got a project that maybe its legacy has been around for 20 years, it's in C, and I'd like to start leveraging some of Zig, I could make my existing project compile with the Zig toolchain, and then I could start implementing new features in Zig?
Yes. There's like the incremental path to that would be like step one, there's a Zig subcommand called Zig CC that is a flag compatible interface to Clang. So if your C project builds with Clang, for people who don't understand why I'm making this, I'm prefacing everything with this. It's because C has a bunch of dialects and there's like compiler specific extensions. So some people might write a project that uses GCC specific extensions that are not part of the C standard, but they do work if you're using GCC. If you're using other compilers, they might not work. Some of these extensions also some proliferated and like you find them also in Clang, so they are not part of the C standard, but it's something that you can use and find pretty much everywhere. Some are not. That said, if your project does build with Clang, then you can replace Clang with Zig CC. That's like step 0. Step 1 is you get rid of your makefile or of your CMake file, and you replace that with a build.zig. So your project is still entirely a C project, but now you are using the Zig build system. And if you write everything correctly, what you get from the Zig build system is caching. The build system knows when it doesn't need to rebuild certain things based on what you changed. You get cross-compilation, and you get integration with the entire tool suite of tools that comes with Zig. And then after that, yes, step 2 would be if you are interested in starting introducing some Zig code, then you can start using. You can basically have a compilation unit that is Zig code that you link against in your C code.
That's very cool. Looking at all the drama that happens around bringing Rust into the Linux kernel, sounds like Zig might be a better fit and a better progression if you want to move a newer language. Or do you not want to touch that drama?
Well, I do think that Zig does have a more. I guess the point is, from a very practical perspective, is that you get probably more benefit out of Zig at every small step that you take. So I feel like with Rust, you have this big payoff where everything that is written in Rust that is not inside of an unsafe block is code that you can trust not to do problematic things, right? And so that reduces the surface that you have to be careful about significantly, and that's great. The problem is that's the main benefit. There's also Rust being a newer language. There's also a lot of minor benefits, minor compared to that. I mean, benefits that you get also as you get your way there, for sure. But I would say that's the big selling point of Rust. In the case of Zig, you kind of start getting benefits sooner than that. So you don't have to get to a point where you did the full rewrite and now you can finally enjoy the full benefit. You get more every step of the way. That's for sure. That said, I don't know. I cannot speak for kernel developers. For some kernel developers, maybe memory and safety bugs have been such a bane of their existence that for them, the effort of rewriting things and getting there with Rust is 100% worth it. Maybe it's not. I don't know. That said, yeah, I definitely do not see myself getting involved in any kind of kernel discussion. My perspective is, I don't know, if they want to have Zig in the kernel, great. If they don't, great. It's entirely up to them. There is just like I've seen some of the drama. I've seen people getting burned out. No, no, not for me.
I think that's quite sensible. At the end of the day, they're programming languages, and the Linux kernels are incredibly valuable. We don't want to burn out the people that are doing it. It's very, very stable. There are lots of places we could benefit from the power of Rust before that, I think, without burning out the people that have made massive contributions over the last 25 years.
Within the limits of what I've seen, it seems to me that there are people that are kernel developers who do want to have Rust in the kernel, and there's also people who do not want Rust at all. And so some of the fight, it's like not necessarily to be interpreted as external Rust people trying to push Rust on the Linux kernel, but it's also maybe mainly internal squabbles between different subgroups of people that work on different subsystems in the kernel, some of which are more open to Rust, some of which are more neutral, some of which are more against. And they are, I don't know, trying to sort it out, I guess, one way or another. But I would agree that it is, from my perspective, an open question of how much effort versus reward you will get in the Linux kernel when it comes to Rust. I guess my point is that the memory safety benefits are there, but in practice, they also come with a cost. And the question is, would a weaker guarantee, but also lower cost, be beneficial, be worth it? And I think that's a reasonable engineering question to ask, although sometimes people are not interested in that nuance. They're interested in the absolutist answer of course, you want memory safety at all costs, which is, in my opinion, definitely not a statement you should make seriously if the discipline that you're doing is something that even remotely resembles engineering, because in engineering, the cost of things is always a problem and something that needs to be evaluated.
Absolutely. I suspect the other complication there is when you're getting down to low-level kernel stuff and device drivers, you're going to start introducing probably a lot of unsafe blocks because you're having to access the hardware directly. So some of the benefit may not be there, but we're getting slightly below the level of my expertise now. So to bring us back to something that I'm more familiar with, you talked a lot about C and Clang then and the cross-compilation. So I want to kind of lift up the covers a little bit and learn a bit about how Zig is implemented. So is Zig, top to bottom, all new code written by the Zig team, or are you leveraging things like LLVM and Clang?
So Zig started entirely as a let's say front end built on top of Clang. So the idea would be you would write Zig code. There would be a parser written in Zig that would parse your code. Then there would be semantic analysis that also would be Zig code. Actually, originally this stuff was C++ code. You had C++ code that would parse your Zig code, analyze it, and then produce LLVM IR, which is, let's just say, the file format that you can give LLVM, and then LLVM will produce a optimized executable for whatever target you decide. The benefit of using LLVM is twofold. One is that LLVM supports a ton of architectures, so they basically implement all the code that you have to write to output for Mac OS ARM64, Mac OS PowerPC, Mac OS Intel, Windows ARM, Windows Intel, Linux, blah, 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 etc. So there's a lot of maybe somewhat repetitive, but also different enough that is like, it's a ton of work that you would have to do to support different platforms on your own. And secondly, LLVM is good at optimizing your code. So when you're trying to make an optimized executable that runs fast, LLVM will have all the internal algorithms to take the source code and squeeze out performance out of it. So this is how Zig started. Now, in the last couple of years, we've been working it started with C++ as a C++ implementation. Then Zig became self-hosted. So the Zig compiler started becoming written in Zig. And that was a huge productivity boost. Well, partly because, our thesis is that we don't feel productive using C++. We suffer from the flaws of C++. We don't feel like we leverage well the things that C++ is good at. So we want a different way of doing things. And so writing the compiler in our own language should be a win, right? Otherwise, what are we doing here? But on top of that, there's also another definitely more objective benefit, which was that, previously you had to write everything that if you wanted to write something, you had to write it in C++. And so you attracted people that learned Zig, but then they would have to write C++. And then there was a transitional period where you could write the implementation for the self-hosted compiler in Zig, but then you also had to copy that implementation in the C++ compiler, which we started calling the Bootstrap compiler. Eventually, we abandoned the C++ compiler, and now it's entirely written in Zig. And there's a Bootstrap procedure where basically, I won't get too much into it because it's interesting, but it's a bit of a rabbit hole. But basically, with a C compiler, you just need to have a C compiler in your computer, and then you run a script, and that builds the Zig compiler for you. So no more C++. And in the last couple of years, we have started implementing our own custom backends. So all the work that I mentioned earlier, the one that you have to do per platform, all the combinations, we started doing it. And the reason why we started doing it is, I guess, twofold. One is that, I guess the main problem is that LLVM is slow. It's insanely slow. And if you want to make a release build of your software, it's fine to spend some time running optimizations. That's, I would say, legitimate and what people normally would want to do. But the problem is that even debug builds are slow. Debug builds don't feature all the optimizations that release builds have, and yet it's still super slow. So for us, having a very tight feedback loop when developing is important and very important. And so we want our rebuilds to be for when you're building like a debug build, when you're like developing stuff locally, we want that to be as instant. We would like for that to be instant. With LLVM in the mix, it's impossible. The second point is that by controlling the entire stack vertically, you open the door to implementing features that LLVM just doesn't support. So in our case, the main feature, which also is a puzzle piece towards having a tighter feedback loop, is incremental compilation. So the idea that incremental compilation with in-place binary patching, where the idea is you have a big project, a arbitrarily big project. So imagine that you have something like, I don't know, Chrome, but it's written in Zig. And you change one function, one variable, so you make a limited change. What you would want is only the file that contains that change to be reanalyzed, only the function that contains the change, or the definition that you touched. You would want only that to be reanalyzed. But then it shouldn't end here, because usually compilers have a granularity of compilation unit where basically you reanalyze only a subset of the program, yes, but then there's a final step where you have to take all these compilation units, object files, like different individual units of code that comprise your final program, and they have to be glued together with references resolved. That's the linking step. And the linking is always done again from scratch. But if your project is huge, then the linking is also going to take some time. You can't escape from that. You can write a faster linker, sure, but the amount of work that the linker will have to do is still going to be a function of the size of your project. In our case, what we want to do is binary patching, in-place binary patching, where the idea is, let's say that you implemented a new function. What we do is that when we generated the executable, the debug executable, so we're trading some performance for speed of compilation. The idea is that your debug executable, every time you have a function call, you don't have a direct function call. Every time you have a function call, that turns into a lookup into a table, or, sorry, that's one technique. Now the technique, I'll tell you this technique. It actually has changed. We don't do the table anymore. There's a different method, but I feel like the table is easier to understand on an abstract level. So the idea is every time there's a function call, you look into a table instead, and the table tells you where that function is located. So the idea is that when a new version of that function is compiled into the executable, you can append it at the end of the executable, and then you only need to update that table entry. And everywhere else, let's say you have 10,000 different locations where they all call that function, you don't have to touch them because they all refer to the table every time they want to jump into the function. So that basically means that linking becomes also a operation that doesn't is not affected by the size of your project. And that unlocks the ability to have genuinely arbitrarily big projects to be rebuilt instantly. The best example of this recently has been that, so this is not fully implemented yet. It's still work in progress, but it's starting to be real and usable on x86 64 Linux. So I was developing on a live stream the compiler with another core contributor, and we were trying this stuff out, and we were able to rebuild the Z compiler instantly. For comparison, rebuilding the Z compiler in debug mode with LLVM takes 20, 30 seconds, depends on the machine that you have, of course. And in this case, it was literally instant.
Wow. So in effect, you're trading some on-disk size for just appending that new function on the end of the binary. That's your linking, updating the table entry to point to that. So your binary is going to keep growing, but you get very, very, very fast linking.
Yeah, and it doesn't necessarily even have to keep growing, because the idea is that the compiler in this process stays on all the time. So the compiler never shuts off. It stays on, kind of like you have like a watch. You're editing a website and you keep the static site generator on or something like that. Similarly, just for source code and programs. And so the compiler, by staying on, it also remembers which sections of the executable have been invalidated, so you can do garbage collection in a sense.
All right, cool. You talked about 30 seconds to rebuild Zig. I remember a few C++ projects I worked on that took 45 minutes to several hours to build.
Yeah, that is a big problem. Yeah,
I would have really appreciated much faster compilation for those.
The promise of faster compilation is not yet fully fulfilled. We have still some work to do before this can become generally available, but it's there. And you can see there have been plenty of people who have in their experience, slow compile times are so ingrained in how they see doing this kind of development that they do not believe it's even possible. And they thought that we would fail. So, and that this was like a waste of time, scope creep, whatever. But it's there. Like, you can try it now, and it's mind-blowingly good.
Yeah, that's one of the reasons I really enjoyed using Go. Again,
yeah.
It's very, very quick for that.
Yes, that's a great feature of Go. And we're basically, it's kind of like it's a Go-like experience when it comes to debug builds. Go doesn't have different release modes, right? If I remember correctly. So in our case, we still have those, because in our case, we really do want. It's fine to wait some time to get a very well optimized release build, but yes, a fast development cycle where you don't have to wait between changes is super important. So we're bringing this basically to the systems programming space.
Okay, that's really cool, and it's great to hear that the compiler is now self-hosted. That always seems like a major step in any kind of programming language's journey to get to that point where the compiler is written in the language itself.
Yeah.
Cool. Well, that was a great discussion with Loris. We're going to break it there, split this podcast in two. Join us again for the next podcast, where Loris and I will talk in more depth about how to go about learning Zig.